Okay, that was a one-dimensional problem for you. And fixed points in the ends, Neumann condition in the ends, play around with it. So I'll put out the codes afterwards so you can have them. Now let's go to 2D wave equation. So you will have the same recipe, double derivative equals the velocity square, but now double derivative in x and y. And the recipe actually will be identical to the one that we had here. So I steal it. It's a little too much to program, so 2D. Exact same setup, more or less, but I've changed my area to 10 by 7 in both directions. So I still have Origo in the center. So x goes from -10 to 10, y goes from -7 to 7. My area, xy, using mesh grid. And now I use size for finding how many unknowns do I have. But else, the setup is exactly the same. The Courant number as before, and we print it out on the screen so we can see what we get. And then I have an initial disturbance. This one is a little bit messy programmed. I want to have a two-dimensional cosine wave, both in the y and the x and y direction. So here I just hard-coded it in quite crudely, actually, but it works. So I should have a nice cosine wave as an initial disturbance. Also, the corner points, I just use them here for scales. So this amplitude that I've used as a disturbance, I use to have automatically scaled max mean values in the corners, because these corner points, they will never be addressed. If you look at the double derivatives, how would it be in if you should draw this stencil up now in time? You will have these three time level here. You have n-1, you have n, and you have n plus 1. And in space, well, you need these 2 points in the x direction, and then you're going to need these 2 points in the y direction. So this is now a three-dimensional discretization star. And then you see the corner points when you have a rectangular area. Say this one is the last one that you address, the last live point. Then you are using this one, you're using this one as boundary values, but you never ever use the corner. So here I cheat, I just use the corner as scales. Then we have this new U and the old ones as well. And the recipe, very simple. Just add another dimension to what we had earlier. So here I just have a temporary. These are all the neighbors, I plus minus 1, j plus minus 1. And then my new one equals the old one multiplied with this coefficient. Now I'll have 4 times the center point from the double derivatives, since you have one in x direction, one in y direction. c square for all these neighbors, and then minus the very old point. So it's the exact same setup. But to plot it, of course, I use surf instead now of plot. So let's see how this one looks when we run it. I now have a Courant number of 0.7, my choice of time step. So this is the area, everything equal to 0, and then my initial cosine disturbance. And here I just use these two corner points as a sort of a scale. The first time step, it's the scale doesn't work because my initial disturbance is very high indeed, too high. But he will levels out afterwards. If you flip it around, there you have it. From above, you see everything is just constant except this initial disturbance located at this point. So let's release him. So there you see now the waves hitting the walls and reflects. The boundary conditions now, I haven't done anything. I just avoid them, meaning you have zero wave, zero motion at the boundaries all around. Everything is zero, is Dirichlet conditions. So from the nice initial disturbance, we have a whole lot of noise. But again, the amplitude so overall doesn't seem to explode, it doesn't grow. So the energy is kept, it looks promising. So if I now increase the time step here, I mean, we had a Courant number of 0.7. The Courant number should be able to be close to 1. So we go a little bit above here. That was obviously a very bad idea. So what happened? Unstable. So what's the criteria? What's the criteria now? What has happened? Well, look at the recipe. We have the double derivative in time, so uij n plus 1, uij n, 2 of him, plus uij n minus 1 by delta t square equals a0 square, and then comes both the double derivative ui plus 1j n 2 times uij ui minus 1j n delta x square, and then the exact same recipe but now in the y direction. So it will now read uij plus 1 n minus 2 times uj n plus uij minus 1 delta y squared. And now for simplicity I said delta x equals delta y, so I only have an h there. Can be put outside. You get the Courant number square in front as before. And what will the recipe look like? You isolate him. uij n plus 1 equals, and you only look at the first point here. What's the coefficient for him? You have the minus 2 here, thrown on the other side, will be plus 2 as before. But now I have minus 2 here and minus 2 here. And when delta x equals delta y, that will now read 4. And then you have C Courant number square, like that. and then for the other ones. So all coefficients should be positive. Now you see Courant number can't be 1. This is going negative. So what will the correct value be? C has to be smaller or equal. What will it be? Square root of 2/2. What's square root of 2/2? Well, square root of 2 divided by 2 should be 0.7071. So let's try that one. 7.07071. There you are, just on the limit. And then if we go a little bit above, I don't think he can take it. He's quite sensitive. Starts out okay. Maybe he survives. Actually he did. That was boring. I wanted him to explode. We need a little bit bigger. 0.8 then. Oh yeah. So you see, square root of 2/2 seems to be the correct stability criteria. So that should be a good exercise for you guys. Check it with von Neumann. It's a linear equation, shouldn't be too hard. So clearly, yes, we have to be below this Courant number criteria as a stability criteria here. For this version here, I have given you the Dirichlet condition, and actually you can see it as well when it hits the boundaries. The values stay 0. You could use the same problem now and introduce von Neumann condition on the boundaries. It's not that difficult. You can sort of do the same logic as we had the last time. You want a derivative equal to 0 on the boundaries. Then actually here we only operate with double derivatives. So how can we think? Well, we are addressing, say, on the boundary, the point ij, so one cell away from the boundary. Then you will address the boundary with either one of these neighbors in space. One of them then will hit inside the boundary. So there we just say this one will now be equal to the neighboring point. Then you will have a derivative equal to 0 here between those 2 points. And I believe I did that one as well. To the Neumann we have here. So a little bit more programming, of course. So for the innermost here, I now have to switch from 3 to Imax -2, and same in the y direction, and then take these two specially around the entire boundary. So the only thing I've done actually is to change this temp, then that this either +1 or -1 is now equal to the one in the center. That's all. But the effect is clearly visible. So now you see the sides also can have motions up and down. you get the overall final picture. A lot of waves going back and forth, little random pattern in the end. And then you can ask, would this be the correct solution? I mean, you start with a nice harmonic initial disturbance, a cosine, and then we get all this rubbish in the end. Why? But it's a rectangular area, so you might say anything hitting in the corner will be breaked up into all different Fourier modes, high frequent, low frequent, so in the end you'll just end up with a mess like this. So that is not so nice. Okay, any questions so far for the 2D wave? Finally then, as a test case, instead of a square area, imagine you have a swimming pool which is not square, but it's elliptical. Not circular, has to be elliptical. Then you will have the distance here, well, that's actually 2b, and here then 2a for an ellipse. Then you have the equation like this equals 1. And what's interesting with an ellipse for this scenario is the fact that you have two focal points. You have one here and you have one here. And the focal points, if you say you want to have the distance from one of them to the other, either way, except just along the axis, if you go in this direction, you reflect, and at that angle you will hit the other one directly, no matter what. And if you take another angle, you can take this one direct, and again you will hit it. And the way you could draw an ellipse, you take a piece of a string, attach it at 2 points. The string must be longer than the distance between those 2 points, of course. And then you put a pencil on the string, keep it tight at all times, and then you just draw up the ellipse. Meaning, regardless of choice of the direction from one focal point, the distance to the other one will be the same, no matter what. Meaning, if you start here generating surface waves, they will spread out, they will hit the wall, but they should then all again meet on the other point. So, if you have a linear surface wave in your swimming pool, which you don't have, but imagine, then you have a sort of a diving board here, and a person dives down into one focal point. What's going to happen? Well, you will then have a liquid diver jumping up from the surface on the other focal point. That should be the theory. Okay? What's the distance to the focal point? F. Well, here my A is bigger than B, so it will be something like this. So that's simple elliptic theory for you. So now let's see what happens. Ellipse, like that. How to design an ellipse? Well, here we are in trouble because so far we have been dealing with finite difference on a rectangular mesh. We are living in a Cartesian coordinate world, and we are going to continue doing that. But how can we then describe an elliptic boundary? We can't. and I'm not going to either. So what I'm going to do is to use my rectangular mesh system and let my surface go straight through. Here is my boundary now, and here are my live points. I have 3 of them, and all of a sudden I have some boundary points inside a solid wall or whatever. How to deal with this one? Well, in this code I'm going to give you, you will see how I have cheated. Here I just create a matrix E. Just say the equation for the ellipse, but then I don't write him on the form equal to 1, I say he's smaller than 1. So that means if x and y are inside this ellipse, this will be true. And in MATLAB, true is 1, false is 0. So this E matrix will sort of be my indicator whether the cell is alive or outside the ellipse. So very easy. And also here I changed the numbers to 10 and 6. That was sort of convenient, because then the distance to the focal point should be 8. You have 10 square, 100, minus 6 square, 36. Then you are left with 64, and then the square root will then be 8 exactly. So I switched the numbers there a little bit. The discretization will again provide us with the demand for stability. Coulomb number must be smaller than square root of 2/2. That's the same. And then I put my initial disturbance exactly at the point where I want it, at one focal point. I had to search a little bit for it, but I think it's correct. So I can show you the initial state now. If we run this one. I have added 0.2 for the surroundings, just so we see that this, yes, we have an ellipse. I have my cosine initial disturbance. If we flip it around, you can see it more easily, like that. And the position in the center of the disturbance should then be at the focal point. You see, -8. I could have chosen the other one as well, but I choose this one. -8, and of course y 0. That should be in the dead center of my disturbance. Then the rest of the code is as before, no change, except I have this one. If he is alive, if this E matrix is true, if it's 1. So you could have said if this one identical to 1, but I mean it's a logical matrix. Should read so as well here. Where is he? He's not listed. Why not? Haven't we created him yet? Yeah, there we have him. You see he is 121 by 201, logical. So he doesn't take up that much space in memory if you're going to do this on a big scale. I mean, if you now write whose, so this huge matrix is logical, only needing one single byte to describe it. So here everything will now be 24,000. If you look at real numbers, u, nu, u, and all of these, you see they are 8 times as large. So logical, they don't need much space. And I mean, if you print him out, you get a whole bunch of zeros and ones. You have a neat one if you want to investigate how a matrix actually look. You have something called a SPI. You write SPI and then the matrix. SPI, he will give you a graphical view, setting a point where he is true and then nothing if he is a zero, meaning true or have a number. So if you want to investigate a matrix, how does it look? Where do I have something different from zero? Then use SPI. That's very, very nice. Okay, back to the program. So the only thing different now, if he is alive. And now, as you see, I don't pay any attention to the boundaries at all. That could be hard to find even. You can, but a little bit tricky. Then first you have to check if the cell is alive, and if it's alive, is any of the neighbors dead? So if that's the case, then you have to then program the boundary conditions there. But here, since I don't do anything, and I have initially everything equal to 0, then I have Dirichlet conditions. So very easy. So now let's see if we can now get this initial disturbance should then pop up perfectly on the other focal point. Not exactly, no. There was something there, but no, definitely not perfect. And if I continue now, I've stopped him on purpose so that we can sort of step him a little bit further. So you almost get it back here after 43, 44, I think. Fairly close to what we started with. But not perfect, no. So if we had done this one correctly, we should have got the same initial disturbance perfectly back. Clearly, the boundaries are not correctly solved here in this problem. So no, we can't really do it like this. We can't have this arrowed on the boundary. So what I actually have now is a boundary. It doesn't look like this at all. He's going to look something like this. Very crudely, as you can see. If you zoom into the boundaries, no, they are not smooth at all. You can't really do this with Cartesian coordinates and a structured mesh. Here we could have used some form of not polar coordinates. We could have used some elliptical coordinates. That would be possible, but rather heavy. We could have used an unstructured mesh system. That is actually something you should be aware of. I can show you. If you have installed everything in all the toolboxes in MATLAB, you have something called PDE tool, partial differential equation tool. That is sort of a separate program where you can play around with partial differential equations, and it's a sort of a GUI system here. So now I can create a domain just using the mouse here. Say this is my area, and I want to solve this area using one or the other of partial differential equations. And also what's nice here, you have a button, make a mesh. Then he will create a mesh for you. using triangles. This of course means you solve the partial differential equations numerically on an unstructured triangular mesh, which is a little bit outside the scope of this course, but here feel free to play around with it if you want, and you can make it finer and finer and finer, and having a lot of fun with it if you want. Here you now have to, if you want to use it, you have to specify first what kind of equations are you going to solve. PDE. So you have elliptic equations, parabolic equations, hyperbolic. So now if we make it easy, just say he's elliptic, and the coefficient here, everything equal to 0. Then we will have a Laplace equation, double derivative in both directions equal to 0. That's okay. Then for the boundaries, we only have one boundary, and here it says now everything equal to 0, so that's okay. And then setting the grid, and you find the solution. And here is the solution, and of course everything is constant. I have double derivative equal to 0, and I have no boundaries different from 0. If you want to have a new one, just to see that it works, create a square like this, and then for the boundary, all these equations first, everything equal to 0, and that's okay. Say the boundary conditions, say this value here is 1, and the value here is 0. This one down here we can say Neumann condition equal to 0, and this one Neumann condition derivative equal to 0. Mesh and solve. So there you have the solution, and you can plot it in 3D if you want. Color map, cool, jet. So there you have the solution. So yes, something that you can play around with. If you want to solve it using this tool, you can. Actually quite fun. Should it even be possible to solve this equation here? I haven't tried it, but it should be possible. Also, what should be possible is from the PDE tool, you can take the mesh that you create and export it into MATLAB and start playing around with it here. But that means finding a discrete version on an unstructured mesh, which is a little bit outside this course, but possible. Any questions from you? I thought it was so nice, this swimming pool idea, but no, I don't hit the perfect match on the other side here, but close. Okay, then I don't have anything else for you today, so we stop here.